Hello, geometry students. Mr. Zacek back and better than ever. We're rolling, rolling, rolling on a river. And we are finishing up Unit 9 today with our last lesson on similarity transformations. Okay, so a similarity is a composition of rigid motions and dilations can be used to understand similarity. So these are the two components, dilations, and a dilation is the key component. A composition of rigid motions and dilations map pre-images to similar images, therefore they are called similarity transformations. So here is a key idea. Two figures are similar if and only if there is a similarity transformation that maps one figure onto the other. So again, the key to this is that there is a dilation. So if two figures are similar, then there's a sequence of a rigid motion, of rigid motions, could be more than one, and a dilation. It has to include a dilation that map one figure onto the other. If there is a sequence of rigid motions and a dilation that map one figure onto the other, then the two figures are similar. A sequence of rigid motions and a dilation is called a similarity transformation. So we have congruence transformations, which we looked at before, which are only rigid motions. And now we have similarity transformations that map one image onto the other, but it has to include a dilation in order for it to be a similarity transformation. So we have triangle DEF has these vertices. So we've got D, which is 2, 0, E, which is 1, 4, and F, which is 4, 2. Okay, and remember we're going to do this one first and this one second when they're written in that order. So we're going to first reflect it in the y-axis. We get D prime, E prime, F prime. So if we plot these points here, 2, 0, that'd be D. E is 1, 1, 2, 3, 4. E is 1, 4. And F is 4, 2. Okay. And we want to translate that across the y-axis. What happens when you translate across the y-axis is that your x-coordinate changes. So it's going to be negative 2, 0, negative 1, 4, and negative 4, 2. In other words, we just come over here, and then we've got F would be negative 4, 2, and D would be negative 2, 0. So that'd be D prime, E prime, F prime. And then we have a dilation. That's the next one. So now we need to do a dilation. And again, in this particular dilation, I don't know why that thickness changed. D double prime, E double prime, F double prime. When they write it with just D and 1.5, we're assuming that the center of dilation is the origin. And so this would be just, we're going to negative 2 times 1.5 is negative 3. Okay, 0, anything times 0 is 0. So this would be negative 1.5 comma 6. And then negative 6 comma 3. So we're just multiplying the x and the y value. All right, we don't have to graph it in this, but we do want to answer this question, is this a similarity transformation? Okay, and the answer is yes, because a reflection and dilation map the pre-image onto the image and are a similarity transformation. So, in other words, whenever it includes a, I don't like how I worded that, but whenever it includes a dilation, it's going to be a similarity transformation. So any combination of a rigid motion and a dilation is a similarity transformation. That would be a better way of saying that. Rigid motion and a similarity transformation. So let's go ahead and do this next one. So L is -4, 2. M is -3, -3. N is -1, 1. Okay, which one of these are we going to do first? Well, we're going to do this one first, the translation of 4, 2. So we're going to add 4 to the x value and add 2 to the y value. So it'd be 1, -1, and then this would be 3, 3. Okay, from there, we're going to dilate it centered at the origin by a scale factor of 1/2. So when we have a scale factor of 1/2 and we have it centered at the origin, what we're simply doing is multiplying the x and the y value by 1/2. So this would be 0, 2, this would be 1/2, -1/2, and this would be 3/2, 3/2. If you want to write those as decimals, you can. Sometimes when people plot that, they like to do it as a decimal. It's a little easier to see. Okay, let's write this a little neater. So yes, is it a similarity transformation? Because a rigid motion and dilation are a similarity transformation. That's a little neater, a little cleaner. Okay, so yes. All right. So for the next questions, the kind of beginning, I don't know if it's formatted a little differently on yours, but what is a composition of rigid motions, okay, and a dilation that maps RST onto PYZ? All right, so we got to figure out how are we gonna get this over here. Well, as I look at this, the first thing I'm thinking of is, what if we rotated this 180 degrees? All right, and a rotation of 180 degrees would take this point here, and this would make it R prime, and then 1, 3 would become -1, -3. This would be S prime, and 3, 1 would become -3, -1. So this would be T prime. So if we were to do that, that would be the rotation. Now from there, let me show you how to look at this. I'm going to use a kind of a dashed line. A dilation, whoops, come back. A dilation that's centered at the origin here needs to go out and to move these points along here. So what's happening to this distance here is, in both cases, if you look at this, let me give you a little different color here. We're going out 3, down 1, and then we're going out 3, down 1. We're doubling that distance. So it's the same thing if you look at any of these other ones. We're going down 3 over 1, down 3 over 1. We're doubling the distance. So how could we put that together? Well, that's a dilation centered at the origin of 2 following a rotation centered at the origin of 180 degrees. Okay, so that's how we could get, and then of what was the starting one? Triangle RST equals triangle PYZ. All right, and so this one, we're going to get triangle ABC, that's the bigger one, and then we want to kind of shrink it down over to this. Well, what I look at this first, I think, what if we reflect this over the y-axis? So here's our y-axis. Let's see what that would give us. Now, A is 6 away, so if we come over here, that would give us A prime. B is 2 away, so this would be B prime. D is 8 away, so let's go, we'd have to kind of go off the map a little bit to get D prime. And C would be right here, this would be C prime. So do we have kind of the same shape and the same orientation there? We do. Okay, now how are we going to get that smaller? And here's where the way you want to do this is go ahead and draw draw in a line from the origin out through those points. Connect the points, and let's see if what's happening is consistent. And what you'll notice here is that this is a consistent kind of shrink here. So to go from B prime to N, well, that's going to be half the distance. That's the midpoint. You can kind of see the same thing down here, and same thing here, and same thing here. So what we're doing is we're taking that, like, from A prime to M. If you go look from A prime down to M, we're shrinking that in half. So it's kind of a similar, what this is going to look like. It's a dilation centered at the origin of 1/2 following a reflection in the y-axis. And what did that do? That took ABCD and that mapped it onto MNHP. All right, so we're kind of playing around with it. I guess the key with this dilation piece is you draw it out, and most often we're going to draw it out from the center of that place. Okay, now what do we do when we don't have the diagram or the coordinate plane? So 6 says, is there a similarity transformation that maps triangle PAQ to TNO? If so, identify the similarity transformation and write a similarity transformation. If not, explain. Okay. Well, we know that it has to be, so there must be, let me walk you through the thought process. There must be, because triangle PAQ is similar to triangle TNO by the angle-angle similarity. So if we have two angles, we know from our previous work that these things must be similar to each other. Okay, so how could we do that? Well, right now, the first thing that I would do is I would rotate this triangle. So if we were to rotate this along point P, we could get some kind of image that would be like if we move this up here, and let's say now A is here and Q would be over here. And we could do this with a compass, but let's just say that's our rotation. And then what you would do at that point is the way you figure it out is you take your points and you connect them, and the point of intersection, my drawing's a little bit off. I'm going to adjust where Q is a little bit. Okay, Q. and where those lines intersect would be your center of dilation. Okay, so we would, dilate it. We'd have some dilation centered at, let's call this point, I don't know, T or something, centered at point T of some number. We don't know what that number is, okay, following a rotation about point P. And again, we don't know exactly what that degree of rotation is. But the idea is, yes, there is a similarity transformation that could be done. And it's a dilation and it's a rotation that would get us to from one to the other. Okay, so for 7, is there a similarity transformation that maps JKL to RST? Okay, so let's look at our, kind of the numbers that we have. So if we have 10, 12, and 16, we're curious, are these all going to be equal? So 10 would match up with 12, 12 would match up with 16, 16 would match up with 20. So let's go ahead and reduce that. So 10 over 12 is 5, 6. 12 over 16, 4 goes into that. So that would be 3/4. And then 16 and 24 goes into that, 4/5. Okay, those are not equal, so is there a similarity transformation? No, there is not a similarity transformation because the two triangles are not proportional. So we're using this idea that we have previously about what it means for things to be similar in order to identify if there will be a similarity transformation. In this case, it doesn't meet the conditions for side, side, side. Okay. So last one, a new company is using a computer program to design its logo. Are the two figures used in the logo similar? If they are similar, describe the similarity transformation. So what you'd be looking at here is, you're trying to figure out is, if we take and we draw these dilation lines through, like you pick your points and you draw in, whoops, go back. Here and here, you're looking for them. Are they all meeting at the same point? Okay. And so, yeah, it does appear that those are similar. It appears that they are similar because a dilation will map one onto the other. And again, if you ever get one of these questions and it says find the center of dilation and you have the two, that's the way you do it. You just take the pre-image and the image and you draw your lines through, and that gives you what that center of dilation is. And we could, if we had some more information, we could figure out what the scale factor is for that, same way we did it in our last lesson there. Okay, so the difference between congruence transformations is congruence transformations are only rigid motions, and a similarity transformation includes a dilation. So you're going to be asked to explain the difference between those on your assessments and on your assignments and labs. So you really want to pay attention to that language. Again, similarity transformations include a dilation. All right, good luck, good work. Let's finish up here the unit, and good luck with the final quiz. And I'll see you back here in this form in our next unit.